Hi, today's lecture is Discrete Fourier Transform. What's Discrete Fourier Transform? It's one of the most important tools in digital signal processing. It operates on a finite set of numbers or finite segments of a discrete signal, as you see here in this diagram. That's the sequence, but it's defined from 0 up to a certain number here, till n, which is equal n minus 1. We are going to explain it, but it's finite. The discrete Fourier transform of a discrete time function x of n may be viewed as its frequency domain representation and used as a tool to approximate discrete time Fourier transform or Fourier transform. That's the discrete time Fourier transform of the signal. As you see, it's a function of the frequency omega, but it's continuous. However, discrete Fourier transform that we are going to study today, it's function of k, but it's not continuous as this one. It's discrete, and which make it very popular in digital application. How can we perform discrete Fourier transform? First of all, we should know that the signal or the sequence we are going to operate on should have a finite length sequence. We call it n. What does it mean? Let me give you a simple example. Let's say that you have a sequence and that's n equals 0, start n equals 0, and you have a value at n equal 1, another value at 2, at 3, at 4. How many samples do we have? 1, 2, 3, 4, 5. So n is equal 5. What is the last limit here? 4. What is the relationship between 4 and 5? That's equal n minus 1. That's why you will see in this relationship, we just have it. It's from n equals 0 up to n minus 1. That's why. And the length, it means n. And 0 everywhere. So if you want to continue and complete this signal I just sketched, it will be 0 everywhere. It's only defined over a finite length, from n equals 0 to n minus 1, which is in this case 4. And since n equals 5, we are going to call this 5-point discrete Fourier transform. So n here is used to define how many points you are going to use to find the equivalent discrete Fourier transform. All right. So now we talk about the discrete. How can you perform it? That's the formula to change. That's how you convert from discrete signal into frequency, in frequency domain instead of time domain. It's the summation from n equals 0 up to n minus 1. And you multiply the sequence times e power minus j 2 pi k over n. You may say, oh my gosh, there are too many variables. Don't worry. We are going to explain it with simple example to understand how you perform this. But this is function of the frequency. When you make the summation, it's from 0 to n minus 1. When you start to find each component of x, k, also from 0 up to n minus 1. To understand this, let's take a simple example, step by step, how you calculate the discrete Fourier transform of a sequence. Let's assume that we have a sequence x of n equal to 1, 1, 0, 0. And we are going to use an arrow here or underline to indicate when n equals 0. So this element represents x of 0. The second element will be to x of 1, x of 2, x of 3. Okay. So the second thing, what's the value of n? 1, 2, 3, 4. You have 4 samples or 4 points. So n is equal 4. So what's n minus 1? It's equal 3. Here you go. That's 3. How can you perform? I'm going to use the formula. Capital X represent the signal in frequency domain equal the summation from n equals 0 up to n minus 1. N minus 1 is equal 3. So just we are going to do that, replace it by 3. X of n, we'll leave it here because it's changing according to n. Multiplied by e power minus j. Always when you find Fourier transform, e power minus j. And what's coming is different from one transformation to another. But it depends on frequency surely. That will be equal to 2 pi k over n, small n. N capital equal 4. The number of points. Replace it by 4. Simplify it more. 2 divided by 4 is equal to. So we'll just erase 2 and 4 and put 2 in the denominator. Now, when you look at this expression, it's a function of n and k. You ask yourself which one you are going to operate on first. Of course, you're going to operate on the sigma. So you operate in n. And n change from 0 to 3. You will ask, what about k? The values of k. K changing also from 0 to n minus 1. From 0 to 3. 0, 1, 2, 3. What does it mean? We're going to have 4 values of x of k. So first start operating with n. To do that, I will just take it step by step. You start to substitute by n equals 0. So n equals 0, so you have x of 0, e to the power minus j, and all this multiplied by n, which is 0. Plus, start the second value, x of 1, n equal 1, e to the power of minus j. You substitute n equal 1, so it would be pi k over 2. Plus, x2, e to the power minus j. If you put the expression by k 2 over 2, the 2 cancel. Plus x of 3, e to the power minus j, 2 pi k over 2, and n is equal 3. I'm sorry, there is no 2 here. 2 was cancelled before, so that's you have 3 for n. So now I start to look for the value x of 0, x of 1, x of 2, x of 3, and they are given in the sequence, and substitute. That's x of 0 is equal 1, so I replace it by 1. And e power minus 0 is equal 1. X of 1 is equal 1. E to the power of minus j by k over 2. X of 2. X of 2 and x of 3 equal 0. So these elements are cancelled. So I have only 2 terms. So what do I have here? That's x of k in general. What do you know about e to the power of minus j something? Yes, we know that from trig. A minus j theta is equal cosine theta minus j sine theta. Let's do it. So x of k is equal to 1 plus cosine pi k over 2 minus j sine pi k over 2. So you have 2 parts, real part, imaginary part. All right. Now you have expression for x of k. What is the second step? Substitute by the value of k from 0 to 3. We'll start with the first one. K is equal 0. So x0 equal 1 plus cosine, substitute by k equal 0, minus j sine 0 equal 1 plus cosine 0 equal 1, sine 0 is equal 0. So the result is 2. So x0 is equal to second value when k is equal to 1. So x1 is equal to 1 plus cosine pi over 2. I substitute k equal 1 minus j sine pi over 2. Cosine pi over 2, it means cosine 90 is equal 0. So I have 1 minus j sine pi over 2 is equal 1. So I have 1 minus j. K equal to x2 is equal 1 plus cosine k equal to 2 pi over 2 be pi minus j sine pi. That will be equal to 1 plus cosine pi is equal minus 1 and sine pi is equal 0. So the result is 0. The last value, k equal 3, x3 is equal 1 plus cosine 3 pi over 2 minus j sine 3 pi over 2. 1 cosine 3 pi over 2 is equal 0. And sine 3 pi over 2 is equal minus 1 times minus b plus j. So these are the value that you have. Just make it in a table. That's k and that's xk. When k is equal 0, the value is equal 2. When k is equal 1, it's equal 1 minus j. When k is equal 2, it's equal 0. And 3 is equal 1 plus j. So you have the value of the signal expressed in frequency domain. And as you know, you can do two things. You can find the magnitude and you sketch the magnitude with k. And the same thing you can do it with angle. And that example or showed you how can you perform the transformation. I think after we did this example, you understand how you perform the segment. We'll see you in another lecture how to do something more involved.